Well, this is the third and last video on nucleophilic addition reactions. We'll be looking at just two reactions today without much discussion of mechanisms. The Wolff-Kishner reduction, wherein we make new CH bonds, and the Wittig reaction, wherein we make a carbon-carbon double bond in place of a carbon-oxygen double bond. But to review just a little bit of where we've been, we've looked in the last two videos at weak base, strong base conditions with aldehydes and ketones with the Grignard reagents, strong base, cyanide, weak base, with a HCN, acid to have a buffer in this mix of cyanide with HCN. And then the strong bases, aluminum hydride and borohydrides, irreversible reactions being seen with these two, irreversible. And then we switched over to acid conditions with the addition of water, alcohols, and diols. And in the case of alcohols and diols, we saw that we could make acetals if we have the alcohol and diol with a catalytic amount of strong acid, sulfuric acid. We could have acetal formation. And then we finished in the second video discussing amines with slight amounts of acid, pH just 3 to 5, not much acid needed, and we can also have, in a sense, that same sort of acetal effect where the oxygen here comes completely off and we get imines or enamines, where we protonate the oxygen in the carbonyl twice. We do that with acetal formation and with enamine formation. We protonate this oxygen twice that's in the carbonyl. The last video, I'm not going to focus so much on mechanisms, but we're going to pick up with amines and see that amines, we don't have to have acid conditions for them to go to imines with an aldehyde or ketone. So let's start there. I have a benzaldehyde here, and I've gone ahead and redrawn this. This is hydrazine. It's sort of a diamine here where we have two NH2 groups bonded directly to each other, and we have a base, a potassium hydroxide. We have strong base conditions. If we have KOH and hydrazine, benzaldehyde goes completely to, in a drawn out way, goes completely to methylbenzene, where we have two hydrogens here. These are H's. Methylbenzene is formed. We get nitrogen gas. Now this is the driving force for this Wolff-Kishner reduction, is the formation of nitrogen gas. There's 78% of our atmosphere is made up of nitrogen gas, so we can know that it's fairly stable. And this is just water that we've also made. And we get our base back, so it's just a base catalyzed reaction. So I really should just say this is our catalyst. So our reaction products from benzaldehyde are methylbenzene, nitrogen, and water, where we have two of these hydrogens going to the oxygen and two of the hydrogens going to the carbon, and these two nitrogens in the end make nitrogen gas. Well, how does that happen? How do we start? Well, you would think it would start with the strong base and attacking the ketone or aldehyde to make an addition product, because that's where the heat is, that's where the reactivity is in the hydroxide. It's a full negative. You would think that's where it would start, but it doesn't. So let's try the next hottest base, the NH2 and hydrazine, and let's try to follow how this might occur. If we were to take, just so we're going to jump ahead to the imine, but I want to draw, just if I can, underneath here, an important intermediate. So if we were to take, without any protonation of this oxygen, this is basic enough to attack this carbon. These are more basic than oxygens in diols and alcohols. So we can propose that we have a satisfactory, amount or speed of reaction where the nitrogen here, not the oxygen in the hydroxide that's floating around, but this nitrogen can attack. We can move the electrons up, and I'm going to go ahead and show just after the second step, protonation of this oxygen through a proton transfer. So this can attack, and we can have a proton transfer so that the oxygen receives that proton in a second step, we have, I'll put the methyl group here, we have now one of those nitrogens this would be the addition product. This is like the carbonyl amine. Carbonyl amine. Like carbonyl amine. But we've made it without, oops. This is like the carbonyl amine we've seen in the imine and enamine reactions, where we just basically add the nucleophile into the carbon, transfer the proton, and we have our addition product. But what's unique about this addition product that we did not see with acetals, when we added an alcohol into this carbon, this is our carbon, we didn't have an acidic proton, one more on that oxygen that we could rip off. But if we're in base conditions, that KOH is floating around in solution. What can drive the formation of this imine is not the protonation of this oxygen, this is really important, but the ripping off of this proton on the nitrogen that's connected to this tetrahedral carbon. So it's in a sense, this is interesting, it's not that we're protonating to create a good leaving group, we're deprotonating to push off, to force a bad leaving group off. So you only get this acidic proton, of course, if you have a nitrogen coming in to attack this carbon. If this would have been an oxygen who only has one proton, after you transfer the one proton, you don't have another proton here. So this is unique. We can run two imines, not just in acid conditions with amines, but in base conditions. Because if we tear that proton off, and I'm not showing the mechanistic step for that, we can form the imine, kick off the hydroxide that's now going to drive our reaction all the way to the, I guess, reduction product. But it starts by a base catalyzed formation of the imine. That's pretty cool. Okay, I'll stop there with the discussion of mechanism. From here on, I'm just going to go ahead and describe what we see and then move on. So we have a base that's regenerated if this is kicked off. This can start the process of forming nitrogen gas. That's basically what we're doing here. So we're going to start forming nitrogen gas. We have an N single bond. We want to go to an N double bond. How do we do that? If we take this proton off, we get a resonance delocalized negative charge. That resonance delocalized negative charge can be expressed to this carbon, and we're starting to get the double bond. We can then, because we have some water with this base solution, protonate, regenerate our base, and just do it again. Take a proton off, we can now have resonance delocalization of our double bond, or of our negative charge. We can, sorry, not resonance delocalization, apologize. We can just simply have the formation of nitrogen gas in an elimination reaction. So you take the proton, this comes down to a triple bond, this goes down to a carb anion, which is high in energy, but we have driven this in a sort of irreversible way. To make a high energy anion, we had to give off nitrogen gas, and that's bubbling out. So even if this was a slow step, it's irreversible because this is bubbling out. It's not going to bind this again, and then we can simply have that very reactive carb anion, grab a proton, and we have our final reduction product, where we have taken in the end and replaced this oxygen off this carbon with two hydrogens. Now, in my course, you do not have to know this full mechanism for the test, but it's just fun to discuss. Alright, let's go ahead and move to our last reaction, the Wittig reaction, and we'll be done. In the Wittig reaction, and I'm going to move very quickly, we have an ylide here that has a nucleophilic carbon in the phosphorus carbon double bond. We've drawn it as an ionic structure, but you can also see it sometimes drawn as a neutral structure. But this is a very ionic bond. So we can draw that pi bond as if, just a resonance form, it's on the carbon as a full negative. So whether you see it like this or like this, it's still an ylide, a phosphonium ylide. It can attack the carbon in the carbonyl as a nucleophile, and we can start the process of making our alkene, our reduction product, plus triphenyl phosphonium oxide, or phosphine oxide. We can make that as our byproduct. In general, what we're picking on is the desire of the phosphorus to make bonds to oxygens, phosphorus oxides, sulfur oxides. You can drive phosphorus to be bonded to an oxygen, preferentially over that bonded to a carbon. The mechanism is a little more involved than just a single attack. As this carbon is attacking the carbonyl, the oxygen is already starting to make, through a sort of a transitional state, a bond to the phosphorus. And so we can kick off completely this triphenyl phosphine oxide at the same time we're making the alkene. So that's just the Wittig reaction. And if we have to come and think of going backwards, where we have an alkene and we have to propose the ylide and we have to propose the ketone that would make this alkene, you always want to combine the less substituted carbon on the side of this double bond over the more substituted carbon. So this carbon has 2 methyl groups off of it. You want that to go with the ketone. If you have the less substituted carbon, this has only 2 hydrogens off of it, you want that to have come from the ylide. Why? Well, because in the reaction to form the ylide, the Wittig reagent, we have to have a SN2 reaction where this carbon is in the end going to be that carbon that's in a, double bond, or in a very polar double bond to this phosphorus. So it starts off with an SN2 reaction. So it's just easier if this is less substituted. In a subsequent reaction, we add butyl lithium, a strong base, to tear off a proton, and we get our ylide that we see on the previous slide. So we can make our ylide. But again, if we had to walk backwards, please remember you want the less substituted side of that double bond, that carbon that has the least amount of alkyl groups. You want that to be having come from the ylide. Alright, well that's it. I did want to just point out, we've kind of seen similar cases where the phosphorus loves to make bonds with oxygens when we used phosphorus tribromide to convert an alcohol to an alkyl bromide. We were picking on the desire of this phosphorus to pick up the oxygen from the alcohol to make a phosphine oxide, and that allowed us to make our alkyl halides. Alright, that's it. It's a shorter video than most of the rest. Thanks. Bye-bye.